Okay, thank you very much for the introduction and thank you for the opportunity to speak here today. And okay, so everything I'm going to talk about is joint work with Roberto Svaldi, in case I forget to mention it throughout the talk. And okay, so let's get started. And as first thing, let me settle the conventions and the notation for this talk. Most of it will be familiar to most of you, but let's anyway go through this. So we'll work over an algebraically closed field of characteristic 0. So throughout the talk, we can think we're working over the complex numbers. And so let me just remind you, if it were needed, what a pair is. So for the purpose of this talk, a pair will be the datum of X, a normal variety, and delta, an effective Q-divisor. So it may have fractional coefficients, and then the key property is that Kx plus delta is Q-Cartier. So some natural multiple of it would become a locally principal divisor. And once we have a pair, we can discuss its singularities. So singularities of pairs, which will be the topic of today's talk. So if we have X delta pair, what we can study, so we can consider proper birational morphisms, pi from Y to X, so this is proper and birational, and we define a divisor delta Y, not necessarily effective, as follows. So on Y, we choose the canonical divisor that pushes forward to our choice of canonical divisor downstairs. And then with this choice, if we put back Kx plus delta, then we can write it as Ky, and then whatever is left over uniquely determines the divisor delta Y. And as I was saying, delta Y is not necessarily effective anymore, but we can look at its coefficients, and those will give us a measure of the singularities of X delta. And we'll say that X delta is KLT, or respectively log canonical LC, if the coefficients of delta Y are strictly less than 1 for any such pi, and for the log canonical case, we also allow equality. So in a sense, KLT singularities are the best singularities we can deal with in birational geometry, since like vanishing theorems and many useful things still hold in that setup. Log canonical singularities are, in a sense, the threshold past which we cannot really say many meaningful things. And so for this reason, it's important essentially to study where our pair fails to be a KLT pair. And for this purpose, let me introduce the following piece of notation. So a prime divisor E inside Y is called a non-KLT place if the multiplicity or the coefficient along E of the divisor delta Y that we just defined is greater than or equal to 1. And we call its image in X, pi of E in X, is a non-KLT center. And this notion allows us to define the following subset of X, which we denote by NKLT of X delta, and in words it's called the non-KLT locus of X delta, and this is the union of the non-KLT centers of X delta. And we do not bother giving it a scheme structure, but this is a well-defined closed subset of X. And maybe to better illustrate how the story goes, let me briefly sketch two small examples. So first of all, we could consider a cone over a curve of genus 1, and the vertex is the log canonical center, and the corresponding log canonical place is extracted if we blow up the vertex of our cone. And another simple example is, for instance, so this is example 1. example 2, we could consider A2 and the two coordinate axes. And in this case, we have 3 log canonical centers. So we have 3 log canonical centers, the 2 axes, but also the intersection of the 2 axes. So the origin is a log canonical center. And the interesting thing is that there are infinitely many log canonical places mapping to this center, because we can blow up the origin, then blow up intersections, and so on and so forth. Okay, so the idea is that the non-klt locus is important to be understood because, for instance, from the non-klt locus, one can extract interesting information, such as lifting pluricanonical sections. And in general, it's just good to have information on its topology to study the singularities of X. So broadly speaking, the goal for today is to understand the topology of the non-klt locus of a pair, X delta. And the fact is that, in general, it can be arbitrarily bad, let's say. So meaning that it can have several connected components, and the combinatorics that one can attach to these connected components can be very bad. On the other hand, if we put some reasonable numerical constraints on X delta, one is then able to extract some useful information. And the story dates back to work of Shokurov and Kollár, among others. And their work leads to what is famous as the Connectedness Principle. So Kollár and Shokurov. And the principle can be stated as follows. So let X delta be a pair, and F from X to S a contraction. So a contraction is nothing but a projective morphism with connected fibers. And assume that minus kx plus delta is nef and big relatively to S. So it's close to being anti-ample. Then what we have is that the non-klt locus of X delta is connected in a neighborhood of any fiber of F. So the idea is that if we assume this numerical constraint on the positivity of kx plus delta, we're able to conclude connectedness or relative connectedness, if we are in the relative setting, of these locus of singularities. And this principle seems a bit technical, but it has very deep consequences and applications. And just to list a few that are very important, one of them is inversion of adjunction, which is a tool to relate the singularities of the total space to the singularities of suitable non-klt centers. Then, if you think about it, let's say that S is a spec of K, then essentially we are in a weak Fano setup, and so one can apply this machinery to study Fano varieties and, in general, complements of Fano varieties. And just to list one more thing, this machinery has been successfully exploited to show that log canonical singularities are Dubois singularities. So the punchline is that this is a very powerful tool, and it's somewhat reasonable to ask whether this is like the best that we can, whether these are the best assumptions that we can set, or whether we can relax anti-nefness or anti-bigness a little bit. And we can say that this is essentially where the story for this talk starts, but the story starts with like a simple example. So example. So if we drop bigness, so in the previous assumptions of the connectedness principle, and we just assume and minus kx plus delta is only in F, one can come up with a very simple example, which is P1 and 2 points. And clearly by degree, we have that, so in this case, we have that kx plus delta is trivial, so it's anti-F, that's good. But then we have that the non-klt locus of x delta becomes 0 union infinity, so it fails to be connected. And all right, so one can say, okay, so maybe we should not drop anti-bigness, otherwise things go south. But on the other hand, it has been a folklore conjecture in birational geometry that essentially, if we drop bigness but we preserve nefness, this is the only thing that can go bad. So roughly speaking, P1 with 2 points is the only thing that can break the connectedness of the non-klt locus. And to make it more precise, we can state the following conjecture, which has been properly formalized by Haken and Hahn. Although, as I was saying, it was something that was in the folklore, in the topic. So again, the setup as earlier, so let x delta be a pair. And once again, we consider a contraction, so a projective morphism with connected fibers. And let's now just assume that minus kx plus delta is relatively in F for this morphism. Then, if the non-klt locus is disconnected over some point little s in big S, then very restrictive things need to happen. So then we have, first of all, we have that the non-klt locus of x delta intersection with the fiber xs has exactly 2 connected components. So it cannot have more, is a nice restriction. 2, we have that x delta is log canonical over a neighborhood of the point we're looking at, because remember, we are interested in the non-klt locus of x delta, but it may be that x delta a priori could have more singularities than log canonical. But this states that if the connectedness breaks down, then the singularities cannot be too bad. And finally, the last piece of information is that P1 with 2 points has to somehow show up. So we have that étale locally over S. So we may need to do an étale-based change around S. We have that x delta is crepant birational to a P1 fibration with 2 distinguished sections, with 2 distinguished. And this is what in the literature is called a P1 link. So the diagram that one would get is the following. We have x delta. You may want to think that one may need to do a few blow-ups. And at that price, we have that the morphism over S decomposes as a P1 fibration over some base Y. And we have that x prime delta prime is PLT. So if you're familiar, is like some nicer version of log canonical. And delta prime, if we look at its part with coefficient 1, determines two sections of the morphism G. So the idea is that x prime to y is close to being y times p1 and 2 points. And so this is like why we say that p1 and 2 points is the only reason why the connectedness principle falls apart. And let me just say in words that this conjecture is the optimal conjecture that one could formulate as for the connectedness of the non-klt locus, because as soon as we also drop nefness, anything could really happen. And Hakon and Hahn verified it in dimension up to 4, and also verified it conditionally to standard conjectures of the minimal model program. Maybe to better illustrate how you should think of a P1 link, let me write down the following example. So say that we have P2, and say that we have 3 lines of coefficients 2/3 meeting at the origin. So say that these 3 guys in red have coefficients 2/3, and then we also have one guy in blue with coefficient 1. So in this case, our pair exactly has 2 log canonical centers, the divisor with coefficient 1 and the intersection of the 3 divisors with coefficients 2/3. But there is no P1 fibration on P2, and this pair is not PLT. But what we could do is to blow up the origin. So if we blow up the origin, the picture becomes neater, because then what we really have is 2 divisors with coefficient 1, and then 3 divisor with coefficients 2/3. And the 2 divisors of coefficient 1 are horizontal for the P1 fibration that the blow up of P2 at one point admits. So the idea is that one may need to do a blow up of this sort to then find the suitable P1 fibration. And then here we can really think of the total space as being something of smaller dimension times P1 and 2 distinguished points. All right, so like the first result I would like to introduce today is that this conjecture is true. So theorem is something that I proved together with Svaldi, and that has been independently proved by Bierkar around the very same days. And since I spelled out everything in the first slide, I can just say the conjecture is true. So the idea is that we independently verified the connectedness principle here stated. So in a sense, we can say that this optimal connectedness statement for the non-klt locus has been finally settled in its broadest generality. So I guess that I'd like to discuss the proof of this statement a little bit, but I guess that it best fit the end of the talk, so I'll maybe defer it to later. And I'll move on to the second topic that I would like to touch today, unless there are any questions. Okay, so the idea is that this statement essentially tells us that we have settled a very first question about the topology of the non-klt locus, namely, how many connected components does it have? And once that is settled, then one could get a bit more ambitious and start asking more advanced questions about it. And that's where dual complexes show up. So let me first introduce what they are. So dual complexes okay, so before introducing them formally, let me say that these objects are objects that naturally show up in the study of singularities. They naturally show up in the study of mirror symmetry, and they're also important to study the space of valuations of a variety. And like I guess the story can be introduced as follows. So let E, which is given as the union of some varieties EI, be an equidimensional simple normal crossing variety. So we have that each EI is smooth, all of the EIs have the same dimension, and they meet properly transversally. So its dual complex DE is the CW complex built as follows. So let me just be a bit vague. So, oops. So the vertices are in one-to-one correspondence with the EIs. Then we have the one cells will be in one-to-one correspondence with the components, the reducible components of the intersection of two of them, of EI intersection EJ. And I'm saying components because any two of these may meet several times, but each time they meet, they'll define a smooth variety of dimension, strictly one less. And then one can keep going. So for instance, two cells will be in one-to-one correspondence with components of triple intersections, and so on and so forth. And let me just say, loosely speaking, we have that attaching maps are determined by inclusion. So this is a bit vague, so let me illustrate it with an example. But maybe before that, let me observe the note. We have that the dimension of the dual complex is always less than or equal to the dimension of E. And okay, I guess that this is dimension over R, and this dimension is complex variety. And equality is achieved if and only if we have exactly dimension of E of them meeting at the point. Okay, so let's maybe sketch an example of how these objects are built. So example. So say that we have three surfaces meeting transversally. So you could think of the three coordinate planes in A3. So we could have like a situation like this one. All right, another color. All right, so hopefully it's decent enough. So what do we have? We have three divisor. Each two of them meet along a line, and all three of them meet along a point. So then, how does the story go? The story goes as follows. For each one of these three divisors, we will have a zero cell. And okay, so then we have that the red divisor and the green divisor meet along a line. So we will have a one cell. The blue divisor and the green divisor meet exactly in one component, and similarly the blue and the red. And then finally, we have the three of them share a point in common, and so that will determine a 2-cell, and that 2-cell will just fill this, and so this is going to define a standard 2-simplex as dual complex for this configuration. So building on this little example, for instance, one has that for the 4-coordinate hyperplanes in P3, so if you also throw in the one at infinity, determine a tetrahedron because we have 4 times this configuration. So, okay, let's see whether I can accomplish drawing a tetrahedron. All right. Which is homeomorphic to a 2-sphere, and this is something that will recur later in the talk. Okay, so far we have introduced some combinatorial objects, some CW complex attached to a simple normal crossing variety. But what we would really like to do is to attach such an object to a pair. And to do so, I have to introduce what a DLT modification of a pair is. So let X delta be a log canonical pair. One could also do it in the non-log canonical case, but then things would become a bit more technical. So let me stick to this assumption. Then there is a DLT modification for it. Pi from y delta y to x delta x. And what is a DLT modification? So i.e., it is something that has the following property. So this is, again, this projective birational, and delta y is effective. So delta y is defined as in the first slide from today. And then we observe that in general, the divisor delta y is not effective, but with this construction, we guarantee that delta y is still an effective divisor. And then we have that y is q factorial. So it has some nice feature about its divisors. And finally, we have that y, delta y, is DLT. So if you are familiar with that, you know that it's a nice property that sits in between the notion of KLT and the notion of log canonical. It's a bit annoying to define, so let me just say that roughly speaking, you should think of this as being so away from the divisors of coefficient 1 in the boundary delta y, we have that y delta y is KLT. So there is no log canonical center that is hiding away from the divisors with coefficient 1. And the divisor with coefficient 1 Formen is almost a simple normal crossing variety. So generically, it is a simple normal crossing variety, and the failure of being a simple normal crossing variety doesn't really bother us for our purposes. So if you haven't seen this notion before, you may really want to think of it as being a simple normal crossing reduced variety. Okay, so why do we like this construction? Because then, okay, with a little bit of cheating, saying that this is simple normal crossing, then one would can consider the dual complex of this y of the components with coefficient 1. And morally speaking, one may want to think of this object as being a combinatorial object that talks about the singularities of x delta And one could draw a parallel with, for instance, the dual graph of a minimal resolution of a surface. So roughly speaking, it wants to encode combinatorics of the singularity in a similar fashion. But the issue here is that, well, we are not necessarily dealing with surfaces, so the DLT modification is not unique. So it not being unique may lead us to think that this invariant that we want to attach to x delta x is not actually well defined. But work of Defernay, Kollár, and Xu comes to rescue, and it states the following, that the piecewise linear homeomorphism type so it's a stronger, is an even more restrictive version of homeomorphism type of the dual complex of this boundary with coefficient 1 is independent of the DLT modification. And so it is an invariant of our singularity. So this PL homeomorphism is an invariant denoted by, so in the literature is denoted by DMR of X delta, and it's called dual complex of X delta. So the notation reminds dual complex of a minimal partial DLT resolution. So it's a bit too wordy. Okay, so let me maybe illustrate how one wants to think of the fact that it doesn't really matter what DLT modification one takes. So let's go back to our friend A2 with two lines with coefficient 1. And if one builds the dual complex of this object, well, we have two divisors of coefficient 1, and then they meet at a point. On the other hand, one could, for instance, blow up the origin. And if we blow up the origin, then we would get three divisors with coefficient 1. And this would still constitute a DLT modification of our original pair. And if we were to construct the dual complex of this configuration, we would then have 3 0 cells and 2 1 cells. And as you see, these two segments are homomorphic to each other, and one can also show that one can piecewise linearly collapse one of the two pieces here to then retrieve the original segment with just 2 0 cells. And so, morally speaking, this is all is going on if one replaces a DLT modification with another one. Okay, so let's maybe write down a couple of examples of dual complexes. So earlier we mentioned P3 and the coordinate hyperplanes given a tetrahedron. So more generally, we have that if we have Pn and we take the n+1 coordinate hyperplanes, then in the same fashion as it happened in dimension 3, these would give us a dual complex that is homomorphic to an n-1 sphere. And incidentally, let me observe that the dual complex of a pair has dimension at most dimension of the total space -1, because what we're really doing is building a combinatorial object from divisors in our total space, and those have dimension n-1. Okay, so this is like a first common example. Then let's consider a subgroup G of the permutation on n+1 elements that acts on Pn by permutation of the coordinates. Then this group naturally acts on Pn, and it naturally permutes the HIs. So then one can consider Pn and the hyperplanes, and then consider the quotient that we get by the group action, and then one could consider the dual complex of it. And what one can show is that then the quotient, then one gets an n-1 sphere quotiented by the induced action of the same group. And so these are some curious examples showing that we have spheres naturally coming up if we consider a log Calabi-Yau setup. On the other hand, if one considers a pair in general, things can go badly. So effect showed by Kollár is that the dual complex of a pair X delta can be any finite simplicial complex of dimension at most dimension of x minus 1. So in general, as for the number of connected components of the non-klt locus, also the dual complex can be as bad as we wish if we do not put any restriction on x delta. On the other hand, these examples of Pn with the coordinate hyperplanes, they suggest that if we put some restrictions on the positivity of x delta, some nice pattern shows up. And it is conjectured that if kx plus delta is q linearly equivalent to 0, so if we are in a log Calabi-Yau case, then the dual complex of the pair is its PL homomorphism type is the one of a k-sphere quotiented by a finite group G, so G is finite, and k is less than or equal to the dimension of x minus 1. So the idea is that in the log Calabi-Yau case, only spheres and quotients of them can show up as dual complex. And this conjecture, so there is work of Kollár and Shu analyzing this conjecture, and we can say that it is verified in dimension up to 4. And then in general, there is weak evidence. In general, oops, pardon me. So they show a few things, but among other things, they show that the dual complex is equidimensional. And that it is a Q-homology sphere. That is that if we take the rational cohomology of the dual complex, this is 0 in degree strictly in between 0 and the dimension of the dual complex itself. So notice that this this vanishing of the rational cohomologies actually match what happens for a sphere and the quotient, because for a sphere we have that it has non-zero cohomology in degree 0 and in top degree, and then the top degree may vanish for a suitable group action, for instance, if we have a dual complex that is a real projective space. And
sorry, is that top Betti number always the most one though?
Sorry?
Like in the top dimension, you might ask if the Betti number is either 0 or 1, or it could be bigger than that.
Oh yeah, it's either 0 or 1. That's right. So yeah, they also show that H top dimension of DMR it's either 0 or Q. And yeah, that's right. And to connect to what we said earlier, let me say that the equidimensionality of the dual complex of a log Calabi-Yau pair is a direct consequence of the connectedness principle. So idea, we have that the connectedness principle implies the equidimensionality. So this is a bit annoying to set up in general, but let me illustrate this idea with an example. So let's consider P1 and 2 points times P1 and 2 points. Then if we consider the divisor that this pair has, so the boundary consists of 4 lines of coefficient 1. And the idea to show equidimensionality of the dual complex is that one would like to show that the minimal log canonical centers all have the same dimension. And the idea is that essentially this picture always shows up. So for instance, we have that. Let's consider this this red log canonical center and this blue log canonical center. They're not contained in the same divisor, but we can interpolate from one another with this horizontal divisor and with this vertical divisor. And in those two setups, so with that interpolation, we first have P1 with 2 points showing up, where the red and the green are the 2 minimal log canonical centers. And by an induction of the dimension, they will have the same dimension. And then now that we know that the red and the green have the same dimension, then one can do the same thing with the green and the blue. And being able to run this trick, it relies on the fact that what we showed about the connectedness principle, that when it fails, there has to be some P1 fibration and there have to be 2 distinguished sections. And we are using that fact to basically identify minimal log canonical centers as 2 distinguished sections of suitable P1 fibrations. Okay, so the idea here is that so using the connectedness principle for log Calabi-Yau pairs, which was known to Kollár and Xu due to work of Kollár and Kovács, they could prove interesting facts about the dual complex of a log Calabi-Yau pair. And so the natural idea now is to then apply what we have showed about the non-klt locus of an anti-F pair and see whether one can have similar nice expectations about the dual complex of an anti-F pair. And that's where the story leads us. And this is the second theorem, maybe not in green, of today. So again, due to myself and Svaldi. And the theorem goes as follows. So let X delta be a log canonical pair with minus kx plus delta F. Then we have the following analogous statements. We have that the dual complex of X delta is equidimensional. and that we once again have Q homology sphere. So the HI of DMR X delta with coefficients in Q is 0 if I is strictly between 0 and the dimension of the dual complex. And furthermore, what we can say is that if anything interesting happens, then we have to be able to reduce to the case of log Calabi-Yau pairs. So we should be able to retrieve the setup of Kollár and Shu. So more precisely, furthermore, if the dual complex DMR X delta is not collapsible, which is a stronger version of contractible, there exists a DLT pair F delta F and a finite group G such that the following two things hold. We have that KF plus delta F is Q linearly equivalent to 0, so we are back in the setup analyzed by Kollár and Shu. And the second thing is that up to the action of the group G, the dual complexes are the same. So DMR of X delta, its PL homomorphism type is the same as the dual complex of I called it F delta F, quotiented by the action of G. So for instance, if one is interested in studying the question whether the dual complex is a sphere quotient, then this shows that one can, then the question essentially reduces to the log Calabi-Yau cases. And let me give you an idea of how this statement is proved. So the first fact is that, so we have the connectedness principle that we show that also takes care of anti-NF pairs, implies the equidimensionality. In the same way as the example of P1 times P1. And then as for reducing to a log Calabi-Yau pair, the idea is that one can replace, so following the ideas of Kollár and Shu, one can replace X delta with a model, let's say X twiddle, delta twiddle, that admits a fibration F over some base Z, where all components of the part with coefficient 1 of delta dominate Z, and X twiddle delta twiddle is DLT. And one can show that if this in this setup up to a quotient, the dual complex is computed by a general fiber. And that's where the F shows up. And the group action essentially measures the discrepancy between what we see on the geometric fiber, which is really picking up the dual complex of X twiddle delta twiddle, and what we see on the geometric generic fiber, which is the same that we would see on a general fiber, and then there is the group G showing up for that reason. But furthermore, we have that if KF plus delta F is not Q equivalent to 0, then it is not pseudo-effective because it has to be anti-NF. And then one can assume that F is a Mori fiber space. And once you are in a Mori-fiber space setup with all components with coefficient 1 dominating Z, we know that they all have to intersect each other because of the Mori-fiber space condition, and then one can argue that the dual complex is collapsible. So these are the ideas behind proving this generalization of the result of Kollár and Shu. And I guess that I have a few minutes left, and I guess that I would use those to then give a sketch of the proof of the connectedness principle. And I guess that that will motivate why there is the word generalized pairs in the title, which I haven't addressed yet. So sketch of proof of the connectedness principle. So we can say that the step 0 is to work with generalized pairs. So that is, so what do we have? We have that minus kx plus delta is relatively in F over the given base S. And what we do is to define M to be minus kx plus delta. And now this gives us an additional piece of structure, which is an F divisor. And so we have that X delta plus M is a generalized pair. So a generalized pair is something a bit more general than a pair together with a relatively F divisor. The F divisor can only just be a BNF BQ Cartier divisor, if you're familiar with that language. So the idea is that in general, M may just be the push forward of an F divisor living on some birational model of X. But what's the punchline here? The idea is that minus kx plus delta F over S is not birational invariant. It's not birationally stable. So if we were to run a minimal model program on X, we may lose this property here, depending on what MMP we run. Yet, we have that kx plus delta plus M being relatively trivial over S is stable under the MMP. And that's why one wants to work in this broader category. Instead of considering pairs that are anti-F over a base, one then gets to consider generalized pairs that are relatively trivial over the base. One has to work with something that is more general and a bit more subtle than a pair, but then one gains a condition that is a birational invariant. And this is, I guess, one of the main ideas of the proof. The second thing is that showing that the MMP or suitable MMPs on X preserve the number of connected components of the non-klt locus of X delta, that's bad, which is also the non-klt locus of the generalized pair, which can be defined in a very similar fashion. So essentially, this allows us to run suitable minimal model programs to improve the geometric situation of our fibration. Then the next step is saying that if a component of the non-klt locus dominates the base, we win. So remember, we are working under the assumption that the non-klt locus is not connected. So like as a little sketch of this setup, so what do we have? We have X here, we have S here. Up to a DLT modification, we can assume that everything is divisorial. So here we are assuming that there is at least one connected component of the non-klt locus that dominates the base. And then we may have, a priori, several other ones that may also be vertical. And we would like to conclude that there are just actually two of them, and they're both horizontal. So the idea here is that since we have d1 that is horizontal, we have that kx plus delta plus m minus epsilon d1. This guy is equivalent to minus epsilon d1 over s, so is not pseudo-effective. And so the idea is that by running MMP, we may assume that F is a Mori fiber space. And here we also use what we said earlier, that the MMP preserves the connected components of the non-klt locus. So what do we have? We have that F is a Mori fiber space, so D1 is relatively ample, and it cannot touch some other divisors, D2 and D3. But well, the only case when a divisor does not touch, an ample divisor does not touch other divisor is the case of curves. So this thing has to be a P1 fibration. And well, for dimensional reasons, these guys, D2 and D3, better be horizontal, because otherwise they would intersect D1. And for degree reasons, because K plus delta plus M has to be 0, there can only be two of them. So this situation cannot happen, and we only really have D1 and D2 horizontal, and there is no D3. And the last thing to do, which is the harder part of the proof, is to rule out something as follows. So it's to rule out that we have several connected components, all vertical. So for simplicity, let me just like draw two of them, and let's assume that they are disconnected by some other component E, along which the boundary does not have coefficient 1. And so we have to rule out this configuration. And for simplicity, say that the dimension of S is equal to 1 for simplicity. Then what one can observe is that in this situation, we have that Kx plus delta plus M plus epsilon for some small number E. This is Q linearly equivalent to epsilon E itself relatively to S. And notice that we can add epsilon E without introducing further singularities, because we are assuming that E does not have coefficient 1 in our DLT pair. So essentially, this adding epsilon E is a legal move that does not change the non-klt locus. Okay, but once we are here, what is epsilon E? Epsilon E is a divisor that is contained in a fiber of a fibration over a curve, but is not the whole fiber. And this is a standard fact in birational geometry, that if we run an MMP on this guy will be contracted. So if we run an MMP on this, and MMP on it, we contract E. And what happens is that we have to connect D1 and D2. But by 2, this is not possible, because 2 granted us that running the MMP would not connect distinct connecting components of the non-klt locus. So it's not possible that we succeed in connecting D1 and D2. And so this in turn rules out the possibility that this configuration actually occurs. So time's up, so let me stop here. Thank you.